All right, here's the second watershed problem, and actually it's a whole lot easier than the first, mostly because everything's in the metric system. So let's read the question. We have a basin here, a watershed, a catchment, drainage basin, and we're given precipitation, right? And we're given ET, and we're told that the change in storage is essentially zero, and our job is to calculate the runoff in that basin. So let's review what that means. So in general, remember the storage equation for a watershed can be written as the change in storage over time is equal to the inputs, which are precipitation, excuse me, plus, let's include everything in here, groundwater in minus the outputs, which would be evapotranspiration and stream flow and groundwater out. And recall that we often assume that the groundwater in is essentially negligible. We ignore it. In this particular case, well, we'll come back to that. So we ignore groundwater in and we lump these two terms here into what we call runoff. So we can write the storage equation then as, let's see, we can write it as delta S over delta T equals P, that's precipitation, minus evapotranspiration, minus runoff. And runoff can therefore be seen when the storage is zero as the excess of precipitation over evapotranspiration and is often considered to be the water that's available for human use. So in this case, it's a pretty simple problem. The only trick maybe is that we're given, once again, as always, we're given precipitation and evapotranspiration in terms of rates, and in the metric system, these are very commonly as millimeters per year. And we're going to need to turn those into volume per time so that we can use the equation. Now, let's write the equation we're actually going to solve here. So in our particular case, this is zero, right? So in our particular case, we can write that 0 equals the volume per time input of precipitation minus the volume per time output of evapotranspiration minus the volume per time output due to runoff. And we can solve that for runoff real simply, that the runoff is equal to the difference between precipitation and evapotranspiration. So we're really almost there. So first thing we're going to do is convert precipitation. Let's see, precipitation here in millimeters per year. We're going to convert that into a volume per time using this area. And then we're going to convert evapotranspiration in millimeters per year into a volume per time using the same area. So let's go do those next. First thing, we're given the area in square kilometers and we're told to express our answer in cubic meters per year. So I'm going to want to convert this into square meters, which is done as follows. We know that there are 1,000 meters in a kilometer and we have to square that term because we have kilometers squared. And if we carry this out, we end up with 6.3 billion square meters of area. And now we're going to actually calculate the volume per time of precipitation and evapotranspiration by multiplying the rates times this area. There you have the two calculations. Notice once again, as always, that the units are going to cancel, leaving us with meters cubed per year in both cases, right? So millimeters cancel millimeters. All right, and so now we just take the difference between these two, and that's runoff, right? Because we wrote up top here, right, that the runoff was just the difference between precipitation and evapotranspiration in the case where the change in storage is zero. So plugging those numbers in, this is what we get. And our answer is a little less than 6.5 billion cubic meters per year of runoff. Now, the only other thing to do to finish this problem is to convert that into gallons per year, and that's a conversion that I don't think anyone knows. So I just simply Googled convert cubic meters to gallons, and this is what I found. So that's the easiest way to find the conversion. So 1 cubic meter is equal to 264.172 gallons. So using that, I get the absurdly large number of runoff of equal to 1.6910 times 10 to the 12th. That's what trillion, 1.69 trillion gallons per year. And just once again, to be clear, I set up my conversion so that my units of meters cubed are going to cancel, one in the numerator, one in the denominator, and I'm going to be left with gallons per year. So there's my answer in gallons per year runoff, and here was my answer in cubic meters per year runoff.